All right, it's 1:35, so let's get started. Today, we'll talk about resolution and the contrast. For SEM, in fact, for anything you want to look at, you need resolution and the contrast. If you don't have resolution, if there are two people sitting next to each other, you don't know whether there are two people or it's just one blob. If there's no contrast, you can just blend into the background. There's no way to find the features. So resolution and the contrast are two unique things that can make the image visible. Before talking about the details of resolution and the contrast, I want to take a small step back by looking at the types of microscopes. So there are two types of microscopes. The first type is parallel beam. For parallel beam microscopes, there are a few examples. I'm pretty sure many of you have used regular optical microscope before. You turn on the light bulb, you put the specimen underneath, you take a picture. So a classical example for parallel beam microscope is the conventional optical microscope. The second example is TEM. For TEM, you turn on the beam and you form an image from the specimen. So the second example is TEM. In the parallel beam microscope, when you turn on the source, it will just form image instantaneously. So there's no time delay from one pixel to another. When you capture one image, all the pixels are captured at the same time. Similarly, like if you take out your iPhone or any smartphones, you take a picture, this is also parallel beam. You don't do scanning at all. The second type of microscope is scanning focused beam. For scanning focused beam, when you form the image, you actually acquire information pixel by pixel. Depends on the step size, depends on how long you dwell on each pixel. The time you take information from the first pixel will be different from the time you take information from the last pixel. So there's always a delay. A classical example for scanning focused beam microscope is SEM, which is the core of this class. In SEM, you form a focused beam, then you rest the beam on the specimen pixel by pixel to acquire the information. Another example, if you are doing some bio stuff, you may be familiar with the confocal microscopy. In confocal, instead of using electron beam, you use a laser. You use a laser scan on the specimen pixel by pixel. Maybe you guys are too young to know how the old TV sets, how they look like. Nowadays, you have like a flat screen. You don't see the old style TV anymore. When I was a kid, the TV sets used to be like boxes. At the end of the box, you have the cathode ray gun, you have an electron gun. And to form an image on the TV screen, actually the beam rests on the screen. Because it does it so fast, human eyes cannot tell the difference. That's how the images were formed on the old style TV sets. So it's another kind of like SEM or scanning focused beam technique. I want to ask you a question. Assuming you want to do some in situ work, either you want to look at the chemical reactions in the microscope, or you want to do deformation in the microscope. Shall we use parallel beam microscope, or shall we use scanning focused beam microscope? If you have the choice, which one do you prefer? Exactly. So if it's time sensitive, then we should use the parallel beam. Oops, sorry. I also heard from Zoom saying parallel. If you want to do in situ work in an SEM, you have to consider the time lag. So when you deform the specimen, or some chemical reactions happening, maybe the top half, has already completed the chemical reaction or the deformation, but the bottom half hasn't been scanned yet. So there's always a delay. By reducing the delay, one thing you can do is to increase the scanning rate. So on each pixel, you dwell less time, and you can get something somewhat similar to the parallel beam. But if you have the choice, use parallel beam instead of the scanning beam instrument. Sure. One image, like one micrograph, you can spend as short as milliseconds, like less than 1 second or way less than 1 second, up to minutes. If you want to get one super high resolution like image of a large area, then it can easily take 5 minutes. So if you want to do in situ work in SEM, then you reduce the resolution, you reduce the beam dwell time on each pixel, then you get more real-time information. Okay, any questions before we move on to resolution and contrast? Again, this is more like a big picture. Let's step out and look at SEM in the context of other instruments, of other techniques. If no questions, let's move on to resolution, the first part of today's class. We'll give the definition for resolution first. So what is resolution? Resolution is the ability to separate two distinct objects. As the example I told you before, if there were two students sitting next to each other, if I'm very close, I look at you guys, I know there are two students sitting next to each other. But if I'm far away from you guys, maybe I don't have the ability to tell whether it's one student or two students. So the ability to separate two distinct objects is resolution. So the unit for resolution is the distance unit. That's why when we say, the resolution of the microscope is that many nanometers, or the resolution of the microscope is sub-nanometer. So whenever we talk about resolution, we are referring to distance. If we dig in a bit deeper, there are two types of resolution. The first type we call fundamental resolution. For fundamental resolution, it is determined by physics. The classical example is if I use visible light, I cannot see virus. Doesn't matter how well I improve the optics. Because the visible light wavelength is about 400 nanometers. Many viruses are tens of nanometers. You cannot use something with a wavelength hundreds of nanometers in size to resolve something tens of nanometers in size. So this is the fundamental resolution, which is determined by physics. The second thing about fundamental resolution is it's independent of magnification. back to the example when we had two students sitting really close to each other. If I'm far away, I don't have the resolution to tell whether it's one student or two students. But if I get closer, which means if I increase the magnification, gradually I can tell these are two students instead of one student. But the fundamental resolution is independent of magnification. For example, using an optical microscope, doesn't matter how far you zoom into or how much you increase the magnification, you cannot see virus. So this is the fundamental part. Does this make sense? Any questions? Okay, so for SEM, we are focusing the electron beam to a probe that scan on the specimen. So let's draw the schematic. If we have a specimen like that, that's the specimen surface. And we have the electron beam and convert that into a point. So this is focused beam or focused electron beam. If you zoom in, looking at the probe, you will find it's actually not a single point. Instead, it's more like a disk. Okay. The disk is called airy disk. When we show the slides, we will have more information on that. Let me ask you why you cannot focus any beam, like either electron beam or photon, like the light beam, into a single point. Why you get a disk instead of a point?
Because it's always a wave.
Exactly, because you always have the duality. And even for electrons, itself is a wave. You cannot converge something smaller than its wavelength. That's why you get a disk. Very good. Too bad I cannot give you the chocolate. Okay, so for any source, when we converge, we can only get a disk, and we have a finite spot diameter. And in SEM, this is called spot size. Spot size in SEM is different from spot size in TEM. Let's just call D spot. On the instrument, you'll see it's called spot size. Again, in TEM, spot size is a different thing. Then the next question is, how can we relate resolution? Let's call resolution R. To write that down as a function of the spot size of D spot. Let's look at one example. Assume we have two features and your spot is about that size. Can we easily resolve these two spots to tell these are two features? Can we tell them apart? Yes? No? Yes? Yes. So this is easily resolved. Let's look at an extreme example. We have two spots or two features, and they are this much distance apart. Can we use the same spot, same electron beam to resolve these two? We cannot, because they are too close to each other. So not able to resolve, so not resolved. Let's look at the third example. Let me draw the beam first. If I have one feature here, one feature here. Can we resolve these two features? Yes, very good. We can resolve these two features. Very good. Okay, there you go. The reason is because if we look at the signal we collect from each pixel here, assume these are the pixels we get, those spots. If we have the feature, we'll say 1. In the first pixel, we'll have 1. In the second pixel, we'll have 0. The third pixel, we have 1. So we have 1, 0 to separate these two ones. So we can tell these two features apart. So this is resolvable. But there's a special name for that. This is the resolution limit. Because if these 2 points get closer, then it will be more and more difficult to resolve. If we look at the distance, we know this is D, or D spot. This is half D. This is half D. So in total, this is 2 D spot. Thus, so this is called resolution limit. Thus, the resolution of the instrument, or the resolution of the SEM resolution, is equal to 2D spot. In some SEMs, the instrument will actually tell you the spot size, the beam size. In many cases, it ranges from 1 nanometer to 5 nanometers. If you see, like from the instrument, if the instrument tells you the spot size is 1 nanometer, then you know that the resolution is 2 nanometers. If the instrument tells you the spot size is 5 nanometers, you know the resolution is 10 nanometers. If the resolution of the instrument is 10 nanometers, you know that you cannot resolve something 5 nanometers in size. If you have nanoparticles 5 nanometers in size, and your resolution is 10 nanometers, it's not even worth trying. You know you need to either play with the beam, or you need to find a better instrument. This tells you whether it's worth the effort to do the studies by knowing the resolution. The temperature of the specimen, or the temperature, the environment? That's actually a really good question. The temperature mainly affects the vibration, as well as the lens stability. So the temperature will not directly affect the resolution. But if there is temperature fluctuation, then your lens will change and your specimen may vibrate. It's much easier to work on a cold specimen than a hot specimen. If you do in situ heating experiments, there will be a lot of thermal drift. It's usually challenging. Any other questions about the fundamental resolution before we quantify?
Yeah, I have a question. So when we're doing imaging, so we have this finite spot diameter. Is that what we're looking at, or are we looking at the 2D spot?
Can you repeat the last sentence of your question? You said, is that something?
So when we're doing imaging, and then you showed us in the, so we have this convergence, right? And we get the spot, the finite spot diameter. Is that what we see when we're doing imaging on the SEM like screen?
Yes, like if you go to the highest possible magnification, then let me think about how to address your question. Each pixel probably will not be the resolution. For example, if I zoom out a lot, each pixel probably will be hundreds of nanometers, like in the micrograph.
Okay.
But if you keep zooming in, you cannot resolve features smaller than the resolution. Does this make sense? That actually that will lead to the second part of the resolution, the photographic resolution, or the picture resolution. Any other questions? Okay, let's quantify resolution just very quickly. There are many criteria we use to quantify resolution. The one people use regularly is called Rayleigh criterion. So what Rayleigh says is the resolution he calls delta, which is same as what we defined R here. The resolution of the instrument is, or the theoretical resolution of the instrument is a constant 0.61, then lambda over NA. So R and the delta here, that's resolution. Lambda here is the wavelength of the source you use. And NA is something we call numerical aperture. Numerical aperture is a function of refractive index as well as the angle of collection. We'll not go into details of NA, but if we look at the equation lambda by replacing photons by electrons while reducing lambda by replacing photons by electrons. So by reducing lambda, what's going to happen to R? R decreases. Does this mean we have decreased resolution?
Reduce the D spot?
So when we reduce lambda, we reduce R. By reducing R, we're reducing the distance. By reducing the distance, the smallest distance we can tell apart, we actually improve the resolution. So the R decreases, but resolution increases. The value of the resolution decreases. It decreases from 200 nanometers to maybe 1 nanometer. So the value decreases, but the resolution itself improves. So there's a little twist here. NA is called numerical aperture. It's a function of refractive index and collection angle. That depends on the design of the instrument. Using optical microscope, I'll give you one example how you can play with NA. Some people just look at the specimen in air, just like, in regular air, there's nothing in between the lens and the specimen. To improve the, by increasing refractive index, you can put a droplet of oil, and this is called immersion lens. Then by doing that, you actually increase NA to reduce the value for resolution, to improve the resolution. But in this course, we mainly focus on comparing photons and electrons because the change from photon wavelengths to the electron wavelengths, it's so significant, NA does not matter that much anymore. I'll give you the example. For visible light, again, using green light as an example, lambda for green light is about 400 nanometers. For electrons in the microscope, the wavelength is around 0.01 nanometers or even less. You can see orders of magnitude difference between visible light and electrons. One is 400 nanometers, another is like 0.01 or even less. That's why using electron microscopy, you can resolve a lot of features which cannot be resolved using optical microscope. There is a physical limit. By replacing photons by electrons, you're breaking the physical limit. If no questions, let's move on. The second type of resolution is called picture limit or picture resolution. Did I use a circle? Yes, I did. So because whenever we take a picture, it's governed by how good the camera is. When we take a picture, you can view any pictures as a matrix. In each pixel, there's a number corresponding to a color. So I'll say that again. If you pull out your smartphone, take a picture, the picture itself is a matrix. You have along the x-axis, you have numbers of pixels. Along the y-axis, you have numbers of pixels. And on each pixel, there's a number assigned to that pixel. And the number can be represented by the color. The other way around, there's a color assigned to the pixel, and there's a number corresponding to the color. So you're looking at like an n by n matrix. Depending on the resolution of the camera, it can be 100 by 100. It can be 1,000 by 1,000 or 10,000 by 10,000. That's why when you look at the smartphone cameras, it's like that many megapixels. Since the picture limit or the pictures, they have pixels. So the resolution now is dependent on magnification. If you keep zooming in, then more pixels can participate representing a feature. Then you can see a feature clearer and clearer. So this one is dependent on magnification. Let's call R the resolution of the picture, or RPCT, the resolution of the picture. Let's look at two examples. In the first case, we have 3 adjacent pixels. And the first pixel is dark. The second pixel is dark. In this case, can we resolve these two objects? Or can we say these are two distinct objects? Something like this. So we have 1, 1, 0 if we just do binary. We know the exact location, but we'll still say like this is one. Yeah, they are kind of like smeared together, so we cannot tell them apart. So this is not resolved. In the second example, again, let's draw 3 pixels. In this case, we have 1 bright pixel in between, and we can easily tell them apart. So this is resolved. Let's do something similar to what we did with the fundamental resolution. So we know the picture resolution is, we need twice the distance. So it's 2 times the pixel size. That's the picture resolution. And for picture resolution, as we mentioned before, as you increase the magnification, if mag increases, then the picture resolution increases. I took some notes. Actually, I had a look on the internet for iPhone 10. When I first started teaching the class, iPhone 10 just came out. The camera is 12 megapixel. For iPhone 4, which I used for many years, the camera is 5 megapixel. So for a camera with 12 megapixel kind of resolution, it will have much better resolving power than the 5 megapixel camera. So by comparing iPhone 10 and iPhone 4, like these two cameras, we're comparing the picture resolution. We can say iPhone 10 is better than iPhone 4. But the fundamental resolution is governed by the wavelength of the light. You cannot use iPhone 10 to break the laws of physics. If, like, something you cannot see below the resolution limit of visible light using iPhone 10 or using iPhone 4, iPhone 10 cannot help. Any questions about resolution before we move to contrast? All good? Okay. So I use the star, so I'll use the star here as well. The next part is contrast. The importance of contrast is usually underestimated by many users. Contrast is important. Just think about a scenario like a chameleon. Like, why we cannot see it? It's not because we don't have the resolution. It's because the chameleon blends into the background. There's no contrast. That's why we don't see it. We have two students in the class. If you're wearing like a clothes having exactly the same color as the wall, then you can also blend into the background. There's no contrast. So contrast is equally important. Contrast is equally important to reveal features, to reveal microstructures, to reveal microstructural features. So the definition for contrast is the ability to tell two adjacent regions apart. Again, let's draw two adjacent boxes. In the first case, the first box is blue. The second box is also blue. There's no contrast. We cannot tell these two pixels apart. But for the second example, one is blue, one is white, then we can tell them apart. So in the first case, there's no contrast. In the second case, there's contrast. And that's how we tell these are two things, two different things. There are two factors that determines the contrast. So let's write down two factors. The first is the relative change between intensities. Let me give you two more examples. In the first example, we have the color filling in the pixel like that. In the second pixel, we have the color filling in the pixel like that. Can we tell they're similar or not? Let's look at the second example. So the first one is pretty much the same as the previous example. In the second case, so in the first case, it's weak contrast. Let me fill in the empty space. In the second case, it's stronger contrast, not the strongest, but it's stronger. But how can we quantify contrast? Contrast is defined as the difference in intensity over I naught. If we use the first pixel as the reference, it will be the intensity of the first pixel. If it is greater than 5%, then human eyes can pick up the difference. It's amazing how human eyes, how sensitive human eyes can be. 5% difference in the intensity, you can see the contrast. The second thing we have to be very careful about is something we call like intensity relative to background.
I got a quick question.
Sure.
I naught is just a stronger contrast.
Can you say that again? I naught is
The stronger contrast.
I naught is the intensity of the reference pixel. It can be the first pixel, it can be the second pixel.
Okay.
So I here, sorry, I should have written that there. I is the intensity. And which pixel you pick will affect the contrast. So assume, that's a really good question. Assume it's a grayscale picture. So it will be from 0 to 255, from super bright to super dark. Then in between, you'll see the numbers. That's how you can quantify the intensity. Does this kind of make sense? Yeah. Okay. Okay, cool. Another way, for example, in electron microscopy, another way to look at intensity is locally there are how many electrons. I'll give you one example from TEM. If I have a specimen, locally have something blocking the electrons, it will appear to be dark. Then anywhere else, they are pretty thin. So the thin areas will have more electrons hitting the detector. And the thick regions, because it's blocking the electrons, will have less electrons hitting the detector. We can also use like the number of electrons hitting the detector in the thin area versus like the thick area to work out the difference. But for intensity, the most intuitive way is to look at like on a gray scale, how gray it is or how bright it is, how dark it is. Does this make sense? Okay. Any other questions? Let's move on. Intensity relative to background, the rule of thumb is we want delta I at least 5 times greater than the noise. Whatever we do, we always have noise. We always have noise. Doesn't matter, like, you know, receiving the radio signals or like, you know, taking an SEM micrograph, you always have some noise. if the signal to noise ratio is too weak, there will be no contrast. The contrast will be buried in the noise. Assume like, we have some feature here, and that feature is dark, so it will decrease the intensity. If the signal to noise ratio is very good, so we have some noise here in the background, as soon as we hit this region, it will decrease the signal, then it will go back. So this is a good signal to noise ratio example. I just write down SNR, like signal to noise ratio. If the noise is so large, if the noise is so large, even when you decrease the signal locally, the decrease in signal can be buried in the noise. So this is bad signal to noise ratio. To have decent contrast, you need to improve the signal to noise ratio. Any questions about contrast? Today in the lab, I'll show you one example of noise. When you increase the scan rate on each pixel, you're staying so little time, and it doesn't have enough time to collect enough signal, then the noise may overwhelm your real signal. Today in the lab, I'll give you one example. Okay. Any questions about resolution and the contrast before we go to the slides? Okay, so today is the second lecture where we talked about the resolution and the contrast. Let's look at the resolution. We talked about when we focus something to a very, very small probe, we don't get a point, because any particles, they behave like a wave. It has wavelengths. Therefore, when we converge that into like quote unquote like a point, instead of getting a point, we'll get a disk. The disk we get is called airy disk, and it's not a single intensity like profile. You'll also see these rings, kind of like diffraction rings. In the first case, I don't know whether you can tell, there are two spots really close to each other. So there's no way to tell it's one spot or two, one feature or two. Then as you move to the right, you see the two spots getting further apart. Here, somewhat looks like there are two peaks, but still it's more like a big hump. To here, you start seeing there are two peaks. So this is close to the Rayleigh criterion, where the two peaks, they partially overlap, but we start having the ability to resolve those two features. Then this, like, getting further apart, this is very clear. Definitely we have two peaks, we have two features. So this is the physical resolution. This is the fundamental resolution. That's something you have seen before. That's the Rayleigh criterion, also called Arby equation. So resolution D is equal to 0.61 lambda divided by n sine alpha. So n sine alpha is also called numerical aperture. Then let's focus on lambda. By using electrons, lambda decreases dramatically. That's how we improve the resolution. Enough about the fundamental resolution. Let's talk about the physical, the picture resolution. I can tell you, the painting is called School of Athens. Anyone know who painted? Anyone knows who painted the picture? Way after Aristotle. It was painted by Microscope. Okay. In the painting, there were many ancient philosophers. Can people tell, like, these people apart? Can you see it's one person standing in the center, or there are two? We cannot. We cannot, because we don't have enough picture resolution. But by increasing the magnification, can you start seeing there are two people standing in the center now? Okay, then by further increasing the magnification, we get even better resolution. We get better picture resolution. We get better picture resolution. Okay, let's keep zooming in. So looking at the two guys in the center, anyone knows who are these two philosophers in the center? Close, close, very close. One is Plato, another is Aristotle. The one on the left is Plato. The one on the right is Aristotle. If you look at their gestures, now with this resolution, you can look at their gestures as well. Plato is pointing to the sky, while Aristotle is like, down to the earth. So Plato represents passion. That's why it's in red color. And Aristotle represents rationality. So that's in blue. A takeaway message is if you are doing pictures, you are plotting two curves, the best match of colors is red and blue. Visually, it gives you the most pleasing feeling. So if you are plotting like, one control curve, one do some treatment, you can plot one in red, one in blue. This is like, an extension of picture resolution. Okay, we also talked about contrast. This is a photograph, the one in the middle. That's a photograph of the A&M campus. This is zero correction. I used PowerPoint to play with contrast. The one on the left, that's to reduce 40% contrast. The one down here is to increase 40% contrast. If there are features you want to highlight, you want to increase the contrast. Then let's look at a few examples. Look at the shadow. With minus 40% contrast, the shadow is kind of like blending into the background. So you're hiding information. If there is information you do not want to show, if you plan to hide some information, either on purpose or not on purpose, you can reduce the contrast. If you want to highlight certain information, you increase the contrast. You can see the shadow stands out. Another example is the cloud. So the cloud on the top image with the minus 40% contrast, it blended into the background. But the clouds in the plus 40% contrast, the clouds, they stand out. Again, whenever you acquire images or in research, like in general, you always have noise. You always have signals you want to capture. You can play with contrast to hide or to reduce the noise. If you think the shadow is the noise, the cloud is the noise, you want to highlight the building, you want to highlight the trees, then you can reduce the contrast. But if you think the cloud is important, the shadow is important, then you increase the contrast to make them more visible. Okay, back to some arts. So this is Last Supper. I'm pretty sure everyone knows who painted the picture. It's by Leonardo da Vinci. If we look at this painting, it's really calming. It's really calming. In terms of contrast, we see some contrast, but not much. Let me show you another painting, the same theme, the Last Supper, but by a different painter. The painter is Tintoretto. This Last Supper, if you look at the image or the micrograph, the image, the painting, the contrast is way higher compared to Da Vinci's one. In Da Vinci's painting, the contrast is lower, so it's more calming and soothing. But in the Last Supper painted by Tintoretto, the contrast is much larger. The contrast is higher. That gives you an intense feeling. So you can also play with contrast to create certain emotions or feelings.